So, let us say I make a thermocouple and read its value with a millivolt meter and I calibrate it at the ice and steam points. So, I make a thermocouple. So, what I need for making a thermocouple is to have wires of two different materials. Let us say I have a copper wire and a Constantan wire, or a platinum and a rhodium wire or something like that. I connect the two wires which I have. So, I have a wire of one material, I have a wire of a different material. If I connect this, I get a junction. I take this wire again and then I connect this original wire back. So, this is another junction. So, if I have junctions of this kind, I can keep one of the junctions at one temperature and the other junction at a different temperature, and then I will have some voltage between these two ends which I can measure with a voltmeter. And I can find out the value of this and use it to find out the temperature. So, one of these junctions is usually kept in for the purpose of calibration or for the purpose as a reference, is usually kept at in a mixture of ice and water. So, we know that the temperature of this junction is fixed, and then this junction I can move around to, and if it is in say room temperature, it will give me some value of voltage. If I keep it at a higher temperature, it will give me a higher value of voltage and so on, and I can use this to find out the temperatures. But in order to do this, I need to construct a scale. So, what is usually done is that I would take this other junction and put it in stuff whose temperature I already know. So, for example, here it says I calibrate it at the ice and steam points only. So, what I would do is, this is already at the ice point, because this is ice plus water, which is what we call as ice point if it is in equilibrium. So, the temperature of this, if it is in equilibrium, does not change. It will be 0 degree centigrade if it is pure ice and water at atmospheric conditions. So, that is what we call as ice point. And in this junction, I need to create a scale. So, what I can do is I can put this also in a mixture of ice and water, then this should show me 0. So, I can, or if this has some error, a 0 error, it will show me some value. I call that value as 0 degree centigrade. Now, what I do is I take this and I can put it in, for example, a mixture of water and steam, which is boiling, or boiling water at 1 atmosphere pressure. If it is pure water and it is boiling at atmospheric pressure, 1 atmosphere pressure, then the temperature there must be 100 degrees centigrade, and whatever is the value this reads, corresponding to that value, whatever is the voltage it reads, I call that value of voltage as 100 degrees centigrade, and then I can construct a scale. So, whatever is the value read as 0 corresponds to 0 degrees centigrade, whatever is the value read at 100 degrees centigrade, I call that at 100, and if it reads any value in between, I can linearly interpolate between the voltage values corresponding to 0 and 100 degrees centigrade. So, that is how I make a scale if I wanted to, using a thermocouple. Now, what happens is that the thermocouple may not actually behave in this linear fashion. What I am assuming is the voltage of this thermocouple, what I am assuming is that this varies linearly. So, if it varies linearly, I can take two constants and find out the equation of the line. So, for example, at a temperature of 0 degrees, if it gives me a certain voltage, and at some temperature of 100 degrees, if it gives me some other voltage, then I can connect these, whatever is the value here. For example, it gives me a value like this. I can because I have only 2 points, I can only draw a line through it. So, I can draw this line, and then if I want to find out the temperature of something else, I find out what is the voltage there. Let us say the voltage is, for example, supposing this was 2 volts. Of course, these are very high voltages, it would be typically millivolts, but just for the purpose of a quick calculation, let us say this was 4. So, at 0 degrees if it gave me 2 volts, at 100 degrees if it gave me 4 volts, then if I measured the value at some temperature, if it gave me 3 volts, then I know that the temperature there must be 50 degrees. If it is linearly interpolated, 0 is 2, 100 is 4. So, half of this would be 3, which would correspond to half the temperature here. So, that is how I usually would construct a temperature scale. But what we are doing here is we are assuming that this voltage is linearly varying with temperature, and that might not be the case. So, what this question says is I am assuming a linear relation between E and T, and I get some kind of equation for this. Now, if I took this temperature scale or this thermometer and tried to measure the temperature of an object whose real temperature is 50 degrees. So, I now have, let us say, water at 50 degrees, and I put this thermometer inside, it will give me some value of voltage. And supposing in reality the relation between the EMF and temperature is given by this equation, then what would the thermocouple read if the correct expression is this? So, what it says is that I put this into something which is 50 degrees. What is the actual what is the temperature read by my thermocouple? Okay. So, that is essentially what we want to find out. So, the EMF generated by the thermocouple is in reality this. So, what we see is that this is not a linear expression. Okay. So, it is quadratic. So, it is something plus some other function of t square. So, in reality this thermocouple will be something like this, but I am assuming it to be linear like this. So, I can now remove these unreasonable values which I put there. So, at 0 degrees centigrade we can find out what the actual thermocouple will read. If I had done calibration at many different points, I would have got this quadratic expression of this kind. If I done at one more point, I would have got this quadratic expression, and that is how the thermocouple really behaves. But I am assuming that it behaves linearly. So, because I am assuming that it behaves linearly, I will have a difference in the temperature at any other point except for the points at which I have calibrated. So, let us read this again. So, I am assuming a linear expression between E and T. If we use this thermocouple for measuring temperature of an object at 50 degrees, what temperature would the thermocouple read? So, the object is really at 50 degrees. What is the value which I will get by using this linear scale? So, that is essentially what I am asked to find out. So, the correct expression for this thermocouple is here. Where T is in degrees centigrade and E is in millivolts. So, this is a thermocouple will read the correct temperature at all the times. So, if the temperature was say 0 degrees, then at 0 degrees it would read this into 0 plus this into 0. So, it will give me a voltage of 0 millivolts. If the temperature was 100 degrees, it will give me an EMF of this. So, this is these two get cancelled. So, I have 2.33 plus 4. If I take this 100 in, I get 4.67 and 2.33, which I think comes out to be 4 and 2. This comes out to be, I think, 7 millivolts. It comes to 6.99. I am rounding off to 7. Actually, it is 7. So, there is not a problem in that. So, what we see is that in reality this gives 0 millivolt when the temperature is 0. It would give 7 millivolt when the temperature is 100. Now, if the temperature was 50 degrees centigrade, what would this give as an output? So, we can find out that. So, if the temperature was 50 degrees, what would be the EMF it gives? So, it will give me this value. Okay, so, I get a value of about 2.91 millivolt, which is what would correspond to a temperature of 50 degrees. So, if I had known this expression for the thermocouple, and if I had used this, then when the temperature is 50 degrees, what I would measure is 2.91, or in converse, if the temperature, if the value of the voltage was 2.91, I would say that the temperature is 50 degrees. This is what I should do if I knew the actual equation of this thermocouple. But the thing is, if I am just making a thermocouple with these pieces of wire and these two liquids, one at 0 degrees and one at 100 degrees, because I am only calibrating at those two, then I do not know this equation of this thermocouple. So, I am assuming that it is linear. So, if it was linear, then what would be the temperature which I thought it would be? It does not matter what I think it is, the voltage is going to be whatever the voltage the thermocouple gives me. So, the voltage which the thermocouple would give me is still this, because the thermocouple does not know that I am thinking of it as linear or quadratic or whatever. Thermocouple is going to give me whatever voltage it gives. So, now what happens is the thermocouple is going to give me a voltage of 2.91 millivolt when I have this as 50 degrees cent. When I put it in some substance, if the temperature of the substance was 50 degrees centigrade, it would give me this voltage. Now, in my scale, what does this voltage, what temperature does this correspond to? So, if I look at my linear scale, I calibrated it at 0 degrees centigrade, which is the ice point, and at the steam point. Okay. So, I have some equation for my thermocouple. So, I can write this equation in any form, but essentially the point is I have E versus T. So, this is like y versus x. So, my equation would be something of the kind of y equal to m into T plus C, and I am calibrating this thing when my temperature is 0 degrees centigrade. I have some value of some E naught. So, then if I substitute in this, what I see is E naught is equal to 0 into T plus C, which means my C is equal to E naught. When I have the temperature is 100 degrees centigrade, I know the value, I am measuring this is some E100. So, which means if I now substitute in this, E100 is equal to, this is m times 100 plus E naught. So, which means m is equal to, so my thermocouple which I have constructed now reads by this formula, E is equal to E100 minus E naught by 100 times temperature plus E naught. So, this is the scale which I have constructed for my thermocouple. So, if I know what are the values of this E naught and E100, I can find out the temperature. So, now for example, this E naught and E100 I am calibrating here. So, these values should be the same as whatever I get with the other. So, this is my thermocouple which goes something like this. So, this is E naught and the slope is given by E100 minus E naught by 100. So, my thermocouple would give these values, but my thermocouple is calibrated at the steam and 0 degrees ice points, which means at the steam point and at the ice point my thermocouple will give the correct values of EMF. So, what I can also do is compare these values with the values I get from the real thermocouple, which has this kind of an expression. So, this is the real expression of the thermocouple. So, this expression and my expression will match at whatever points they are calibrated at. So, I had here for the accurate thermocouple, I have 0.0467 into T plus this. So, at 0 degrees whatever value this gives and whatever value this gives should be the same. So, we already saw that at 0 degrees this gives 0 millivolt. So, at 0 degrees this also should give 0 millivolt. which means that this E naught over here should be 0. At 0 degrees, whatever I get on this side should be 0, which means E naught is essentially 0. So, I can now replace this E naught by 0, that is one thing which I can do. The second thing is, at 100 degrees at steam point, whatever this expression gives and this expression gives should be the same. We already saw that at 100 degrees this E100 is 7 millivolt. So, this E100 is essentially 7 millivolt and this E naught is equal to 0 millivolt. Now, I can substitute those here. So, what I get is, for my thermocouple I have E is equal to E100, which is 7 in millivolts, minus E naught, which is 0, divided by 100 into T, plus E naught, which is again 0. So, essentially my thermocouple gives me this is the equation for my thermocouple. So, if this value was 50 degrees, in reality what I would get is 2.91. So, getting a value of 2.91 millivolt, what is the temperature? So, the temperature is this, which comes out to be 41.5 degrees centigrade. So, what we see is that because in reality a thermocouple does not have a linear scale, if I assume it to be linear, my values which I get will not match with the real values which I am trying to measure. It will match at the points at which I calibrated, which is at 0 degrees centigrade and 100 degrees centigrade, because that is the meaning of calibration. Because when I calibrate, I know the actual value there and I assign the actual value to whatever I am trying to measure. At any other points apart from the calibration points, there will be an error, and in this case what we can see is at 40 degrees centigrade, or actually at 50 degrees centigrade, when the real temperature is 50, I have an error of about 9 degrees centigrade. So, I can measure the value using this thermocouple which I have made. I can measure the value correctly at 0, I can measure the value correctly at 100 or close to it, whereas in between the error can be as high as about say 20% or so. So, this is one of the reasons why when we buy thermocouples, we would like to buy standard thermocouples which are calibrated over a wide range, where this equation is well known, so that we do not have to assume something to be linear. So, when we make a thermometric scale, these are some things which need to be taken into account.